Let's get into 14.8 just a little bit. This one is Lagrange multipliers. So the last few problems of this that we just did, we could have done it using Lagrange multipliers, and it might have been easier this way. But who knows? Might have been a bit easier. Maybe not, though. But you're supposed to learn Lagrange multipliers anyways, whether it's easier or not, I suppose. And so here's how it works. Here's how it works. This G function is a constraint. And you're supposed to, the idea is you're supposed to maximize or minimize a function f of x, y, z, given the constraint g of x, y, z equals k. Okay. So the last few problems, like I said, the last few problems we just did in the previous section, were pretty much were of this kind of fun, because right here, for example, this is your constraint. It's just not written like a G, because you would have to pull these things over to the other side. So you'd have like maybe x squared plus y squared minus z squared equals 0. That would, and then so x squared plus y squared minus z squared would be your G. And then the function that you're trying to minimize would be f of x, y, z with this z squared right there. So without, but instead of doing it using Lagrange multipliers, we did it by just taking this, substituting in, and reducing this down to having a function in 2 variables instead of 3 variables. Okay. So here, the method here has us leaving it as 3 variables. And the idea is that that's going to happen when the gradient of f is pointing in the same direction or opposite direction as the gradient of g. Okay, that's going to happen. And I'll try to explain a little bit more about that. But the maximum or minimum values are going to, with this constraint, is going to occur when the gradients are pointing in the same or opposite direction. So what you do is you set up this, you set up these equations, and you have this equation, and you get a whole bunch of equations, and you try to solve those. And you have an extra variable lambda, which really doesn't, the lambda doesn't really affect your answer at all, but it's something you have to deal with. And if you can solve for it, great. If you can do it without solving it for lambda, that's great. That's fine too. You don't have to find lambda. Okay. So let me kind of give you an idea of why that's the case. Let's take the distance function, for example. Okay, let's suppose that, I'll just kind of draw a picture here, okay? To try to give you an idea of why this works. Okay, so let's suppose, let's consider we have a point right here, and then we have, let's say we have a curve over here that goes like that. So this curve would be like our g of x, y, z equals k. So that's the restriction. You have to be on that curve. And then your f would be that would be like the distance between this point P, so that's P right there, and any other point, X, Y, Z, okay? Okay, now the distance function, it's the square root of a bunch of stuff. And so if you take different values, if you set f of x, y, z equal to, let's say, 2, then that's going to give you a circle like this. Oops, that's going to give you a circle like that. That's like f equals 2. And then if you set f equal to 3, it's going to give you another circle. Okay, now if you keep expanding these circles until it touches this curve, then it's gonna happen when you're touching right here. Right? This is the closest point on the curve to this point. So when you're going to have a circle like that, and when those touch, the gradient of f is pointing, and for this case, it's pointing in the opposite direction than the gradient for g. Okay? So this is the gradient for g, right? They're pointing in the opposite directions. Okay, so that's where that condition comes in right there. And then, so that's going to happen when you're doing maximizing and minimizing. When this is a smooth curve, smooth meaning it's differentiable, meaning the partials exist and are continuous. And then this is also a smooth curve.